This session is being recorded. This morning we're going to talk about the second half of Chapter 10, and this is going to be the last session as far as doing lectures and live, and then we will have a study session, I believe, on Wednesday, and then you'll have until Wednesday of next week to take your exam for Exam 4. Please make sure that you can take this exam anytime before midnight on the 29th of April. That doesn't mean wait until then. If once you need to get ready and take it, and then that way you'll be done with it, and then we can see if you are going to be eligible to not take the final exam or not. You need to have an A or a B average. If you have a B average, you need to let me know that you are okay with the B and you don't want to take the final exam. So I'll send some instructions on how to do that at the end of this week. All right. And if you have questions about whether you are eligible or whether you should try to take it, then all you have to do is email me and I'll crunch the numbers for you, and I'll tell you if there is an advantage to you doing that. All right, so any questions about the first part of this chapter? If not, we're going to go ahead and move on. We looked at the simple gas laws, the combined gas law, and the ideal gas law when we talked before. And so today what we're going to look at is Dalton's law of partial pressure. And Dalton's law is basically you just add things up. The total pressure in a system is equal to the sum of the partial pressures, that is the pressure associated with each gas that's in there. And the example they have here for you is the composition of air. Air is 78% nitrogen, which is inert, which means we don't really use it. Oxygen, 21%, argon, 0.9, and then carbon dioxide and other things are also found in there. So it's a mixture of these things, and so it's a percentage. And so we can look at it as a percentage, or we can look at it as the partial pressures that are associated with each one of those gases. So Dalton's law says the total pressure of a gas mixture is equal to the sum of all of the partial pressures, okay? And so when we think back on the kinetic molecular theory, remember that they're very, very small, these gas molecules, and they don't really react. And so as long as you don't change the temperature, then all of them have about the same average kinetic energy. And because it's the same, then the total pressure of the collisions is the same no matter what, no matter how big those are. So the pressure of a single gas is called its partial pressure, okay? And you'll write that as P, and then if it was H2, we'd write P sub H2. So that's the partial pressure of hydrogen gas. And we can either calculate it as the number of moles of gas in a container, or we can look at the mole fraction. And so we're going to look at both of those ways, actually. And so if you have a mixture of gases, remember they're not reacting, they're just actually existing together. And so if you have a mixture of gases, the total pressure in that cylinder or balloon or whatever you have it in is the sum of each one of the individual pressures. And so this is one of the easiest gas laws there is, because you just add things. Remember that they're acting independently, which just means they're not interacting with each other. So the pressure due to any of these components, as I said, is the partial pressure. And from our ideal gas law, if you recall, we had PV equals nRT. And so if we're solving for P, we've divided both sides by V, and we end up with P of the gas, whatever that gas is, that's what N means. is equal to nRT over V. So each gas individually in there is going to have its own pressure, and it's going to depend on the temperature and the volume and the number of moles of the gas that you have. And so if you have multiple gases in a mixture, then each one of them will have this formula. And so then when you add them together, all and multiplied by RT over V times N. And so this kind of looks crazy, but all they're saying is that since the total pressure is equal to the partial pressures of each one of these gases, it's also equal to N times RT over V for each one of those gases, right? And since you can use the distributive property, you can add those gases together and multiply the whole thing by RT over V. So the total number of moles times RT over V will give you the total pressure. And so the partial pressures is the same proportion as the mole. Okay. So if you have partial pressure related to total pressure, it's going to be proportional to the moles that you're looking at divided by the total moles. And this is called the mole fraction. And we've looked at mole fractions before. And X sub A is moles of one thing divided by the total moles in the system. So since the partial pressure of one of the gases it is equal to the mole fraction of that gas times the total, okay? So all they're saying is if it's 78%, okay, which is 0.78 mole fraction, if it's 1 atmosphere at sea level, then your partial pressure would be 0.78 atmospheres. And then you could just add them up. These come from those percentages before of 78% nitrogen, 21% oxygen, and then 1% argon. And so you're adding those up, and they should equal the total pressure of 1 atmosphere, okay? So how we use this is that if we know the partial pressures of all but one gas, we can figure out what the partial pressure is of that last one. We do have to keep the temperature the same though. All right, so a 1 liter mixture of helium, neon, and argon has a total pressure of 662 millimeters of mercury at 298 K. If the partial pressure of helium is 341 and the partial pressure of neon is 112, what mass of argon is present in the mixture? And remember, I told you in gases, whenever you see mass, you think moles, because moles is what you can figure out, okay? And then you can always, as long as you know what the gas is, you can figure out what the mass is. So I'm going to take inventory. So my total pressure is 662 millimeters of mercury. The partial pressure of helium is 341. Partial pressure of neon is 112. And so I don't know the partial pressure of argon, right? Okay, so what I do know is that the total pressure is going to be equal to the sum of the partial pressures. So partial pressure of helium plus neon plus argon, right? So 662 millimeters of mercury equals 341 plus 112 plus X, right? And so then 662 minus 341 minus 112 equals X. So X is going to equal 209 millimeters of mercury. So I need to figure out how many moles that is. All right, and so if I'm going to do that, I'm going to use my PV equals nRT formula. So I need this in atmospheres. So 1 atmosphere over 760. And so that's going to give me 0.275 atmospheres. Okay, so now I know the pressure of that. What I need to solve for is how many moles, because if I want to know the mass and I know what the gas is, I solve for the moles, and then I can use the formula weight, and I'm going to be looking at argon, and so the formula weight of argon is 39.35 grams per mole. So I just looked that up on the periodic table. All right, and so then I solve for N. So N of argon is equal to the 0.275 pressure times, 0.275 atmospheres times meter. Told me it was in a 1 liter container, divided by R, 0.0821 liter atmosphere over mole K, times the temperature in Kelvin. It told me it was 298 K. And so I just put that in there. So the number of moles of argon is going to be 0.0112. And then to get the grams of argon, I'm going to multiply that by 39.35 grams of argon per mole. And that's going to give me 0.449 grams of argon. So I used Dalton's law to figure out what the partial pressure of the argon was, converted that to atmospheres because I'm going to be using R, which is 0.0821 liter atmosphere over mole K, right? And I have to have it all in those same units, so that's what I did. And then I plugged that into the PV equals nRT, that gas formula, found moles, and then used the formula weight to find grams. And then I gave you a practice, of course. So I'm just kind of showing you here. Remember that as you go down, every 10 meters you're in an atmosphere. So if you have 1 atmosphere pressure on your lungs at the surface, by the time you get to 30 meters, you have 4 atmospheres. Okay, and notice how this changes the partial pressure of your oxygen and your nitrogen, because basically what you can think about it is that like when we talked about Charles' law, it pushes that gas into the liquid. And so as you're getting more and more pressure on that, it's compressing this gas. And so it's making the partial pressure of each one of those gases rise inside your lungs. So a 12.5 liter scuba diving tank contains a helium oxygen mix of 24.2 grams of helium and 4.32 grams of oxygen at 298 K. Calculate the mole fraction and partial pressure of each component in the mixture, and then the total pressure of the mixture. Okay, so I know it seems like it's got a lot of words and all that, but let's pull everything out and see what it gave us. All right, so it gave us a volume, okay, a volume of 12.5 liters. It gave us the total pressure, right? The total pressure, no wait, it gave us the mix, it gave us the mass, so grams of helium is 24.2 grams. Grams of oxygen is 4.32 grams, and that's the only 2 things that are in there. Okay, So I have to look at it in terms of moles, because when I see grams, I think moles. All right, so I convert these to moles, and helium, of course, is 4 grams per mole, and oxygen is 32, so it's O2 grams per mole. That's going to give me 6.5 moles and 0.135 moles. So at this point, because it's those two added together, because I only have those two. So it's 6.185 moles total. Now it wants the mole fraction of each one of these, right? So the mole fraction of helium is going to be 6.05 divided by the total moles, which is 6.185, because that's what the mole fraction is, right? So that's 0.978. And then the mole fraction of O2 is going to be 0.135 divided by the 6.185. And that's going to be 0.022. And it doesn't have any units because it was moles over moles. Okay, so I can do a couple of things now. I can do the total pressure, right? And then from the mole fraction, I can figure out what the partial pressures are. All right. So what I'm going to do is I'm going to use the total moles, and I'm going to do the PV equals nRT. So I'm figuring out. So I've got moles, so I'm figuring out what the total pressure is. So this is going to rearrange to P equals nRT over V. So I plug in the N value, the total. So P total equals 6.185 moles times R times T. It told us 298 divided by V, which is 12.5 liters. And that's going to give us 12.1 atmospheres. And that's P total. And that's one of the things it wanted, right? So I've done the mole fractions, so there those are. This is the total pressure. And then it wants the partial pressure of each component. All I have to do to figure that out, now I could plug in these two, this number and calculate it, and then this number and calculate it. But it's really easier once I've done this. I know that 0.978 of this is the helium. So the pressure of the helium is going to be equal to the total pressure times the 0.978. All right, and that's going to give me 11.8 atmospheres. And then the pressure of the oxygen is 12.1 atmospheres times 0.022, which is going to be 0.264 atmospheres. And if it doesn't come out to exactly 100.00, that's okay. All right. So if you find the mole fractions, okay, and so you do that by figuring out how many moles of each gas you have divided by the total moles, and it's like a percent, but we don't multiply it by 100. And so then that allows us to get the total moles. You figure out the total pressure, and then you use the mole fraction to figure out what fraction of the 12.1 atmospheres is helium, and then what is oxygen. Any questions about that? I feel like my voice is really scratchy today. So when we're in the laboratory and we're actually trying to do an assay and figure out how much gas is being evolved and everything, we often collect that over water, or we use the displacement of the water. And so I'll have a tube where my reaction is going, and zinc or magnesium with hydrochloric acid, okay? And so when that starts, it's going to start a bubble. And I have this connected with a glass tube, and it goes up into a beaker that's filled with water when I start. And so this hydrogen gas, because I leave this above the surface just a little bit so my tube can go in there. It's going to bubble this hydrogen gas, and it's going to start to fill this area here. And I can then measure this if it's got graduations on it. And actually in the lab when we do it, we have a big graduated cylinder. It's like a 2 liter, or yeah, 2 liter. And we can measure how much that is displaced. And so we can give a direct measurement of how many milliliters we've displaced. And so the partial pressure of the water vapor, though, is also here, because this is a wet environment rather than a dry environment. So if I'm capturing hydrogen gas, it's going to be wet. Okay, it's going to be wet because I am collecting it at this interface of where the hydrogen and the water is. And because I'm doing that, I have to take into account the vapor pressure of the water, and that is it's going to be like a correction. Okay, the only thing that this depends on is temperature, and there's a table that'll tell you partial pressures of water vapors at certain temperatures. Now, on an exam, I'll tell you the vapor pressure of water at whatever temperature the problem is talking about is this, and so you'll have that. All right, and these will be at your measurements and everything will be at degrees C, but remember, you still will have to convert those. So if you collect the sample over water, the gas has a total pressure of 758.2 millimeters of mercury. That's going to be something that you read on a barometer as atmospheric pressure. Okay, and then you look at the water table and the vapor pressure, it'll tell you what the vapor pressure of the water is at that same temperature. Okay, and for example, at 25 degrees, it's 23.78 millimeters of mercury. You're going to leave it in millimeters of mercury while you're doing this, because the tables in America are all millimeters of mercury. So then to get the partial pressure of the dry gas, you would subtract the atmospheric pressure minus the vapor pressure of water at that temperature, and that's your new pressure. And so this is the pressure that you would use to work the problem. The problems are going to be exactly the same gas laws we've already worked problems with. The only difference is when you collect it over water, it'll say in the problem over water or by displacement. Okay, you'll know that you have to do this correction. Plus, I'm going to give you the vapor pressure of water at a certain temperature, which is also a clue that you're going to have to subtract that. And so this is important in these types of problems, and so you won't get partial credit if you don't do this correction. And this is just an example of vapor pressures of water at different temperatures. Notice it changes quite a bit. 23.78 is 25 degrees or room temperature. If you raise that 10 degrees C, though, it goes all the way up to 42. And I mean, it's the hotter it is in degrees C, the higher that vapor pressure is going to be, until it finally gets up here where it's boiling, and notice it's equal to atmospheric pressure at that time. That's when it boils. Okay, so this is going to be a description of something that we're doing in the laboratory, and you know, if we were able to, we would be doing that. If not, then we're just going to have to describe it. I already showed you kind of what the apparatus looks like. So it says, in order to determine the rate of photosynthesis, the oxygen gas emitted by an aquatic plant is collected over water. Okay, at a temperature of 293 degrees Kelvin, 293 Kelvin, and a total pressure of 755.2 millimeters of mercury. Over a specific time period, a total of 1.02 liters of gas was collected. What mass of oxygen gas in grams forms? All right, and I saw grams. All right, so I'm going to take my inventory. So my temperature equals 293 Kelvin. My pressure. Now here's where this comes into effect. Since it's over water, my total pressure is 755.2 millimeters of mercury. I guess I need to put my glasses on so I can write better. The vapor pressure of water at 20 degrees C is 17.55 millimeters of mercury. So I have to correct for that by subtract 17.55, and this is going to be my actual, I think it's calling it torr. Torr and millimeters of mercury, if you recall, are the same. Okay, so it's 737.65 torr. Now that's going to have, all right, so I've corrected that. Now that's the only thing that I do in extra. Everything else I'm working it just like I did before. My volume was 1.02 liters. R is 0.0821 liter atmosphere over mole. Okay. And so it wants grams, so I know I have to do moles first. So, and I've shown you how to rearrange this, so I'm just write moles is equal to PV over RT. Okay, and so N is going to be equal to 0. Oh, so this reminds me that these have to be in the right units, so I've got to convert that into atmospheres. 0.971 atmospheres. All right, so 0.971 atmospheres times 1.02 liters divided by R times T. All right, so then the number of moles is going to equal 0.041. Now, since I know that this is oxygen, okay, and I know that oxygen is in the form of O2, so times 32 grams of O2 in 1 mole. And so grams is going to be equal to 1.32. Don't forget your diatomic gases, okay? So that's why that's 32 instead of 16, because oxygen exists as O2. All right, and there's your one to try. So the kinetic molecular theory, we talked about this during the entire semester, and we talked about it in terms of movement and the gases. Obviously, they're moving faster, they're farther away from each other, they have elastic collisions where they don't trade energy. We talked about that a little bit earlier. Okay, so we look at gas molecules as particles, and they are constant motion, moving as fast as they can to get as far away from each other as they can. Negligible attraction, all right, and they bounce off each other, continue moving in another direction, and there's a huge amount of space between them, okay? So these are all postulates of the kinetic molecular theory that you need to be able to identify, okay? So like in a multiple choice, you've got to be able to pick out, you know, which ones are or are not components or postulates of the kinetic molecular theory. We also know, because of this, that the average kinetic energy, or like the speed even, of the gas particle is directly proportional to the Kelvin temperature. So as I increase temperature, then the kinetic energy increases, right? Now, the collision of one of those with the other, as already said, is elastic. There's no loss of energy, okay? And so the energy is conserved, as we say, because any energy that is lost by one molecule is gained by the other one. But they continue moving. It's not like it stops them, you know, dead in their tracks. So because the particles are moving and striking the container walls, then they are exerting a pressure. All right, and so this creates a pressure, which is force per unit area. And so that pressure is proportional to the temperature and also the velocity of these particles, which increases as you increase the kinetic energy. And so it tells us about this whole PV equals nRT thing, that, you know, these are those relationships that we first saw in Boyle's and Charles and all those guys, as to what, you know, if you increase the pressure, you decrease the volume. If you increase the temperature, you increase the pressure, etc. That whole P1V1 over T1 equals P2V2 over T2. All right. The heavier the molecules are, the slower their average velocity or speed will be. So if you look at the ones that are higher molecular weight, so that's 32 grams per mole. Nitrogen is 28 grams per mole. Water is 18. 4 for helium. And 2 for hydrogen. So this shows you that they are the velocity is going to be lower. Okay, it's going to be lower the higher your molecular weight is. So lighter particles travel faster on average than heavier ones. Okay, and so that's not hard to imagine, and that makes total sense, because, you know, if I have a big old linebacker that, you know, somebody fumbles and he grabs the football and he's going to try to run for a touchdown, he is going to be much slower than a running back would have been, because a running back is thin and swift, and, you know, that's what he's made for, is running fast, and so he's light on his feet. So a heavier particle is going to lumber along, okay? So it's going to be much slower than a light particle is. As you increase the temperature, you're going to increase the speed, okay? Because you're getting those molecules all excited and they're going to start moving faster because their kinetic energy is higher. But remember, heavier molecules are going to have a slower average speed than lighter molecules. This is kind of a cool concept here. We've talked about diffusion before, okay, and we saw diffusion in liquids also. Diffusion is just where the molecules, due to their molecular motion only, are going to spread out, and they're going to go from high to low concentrations until it's all the same. And if you put, like, if you take a glass of water in a clear glass and you put and just drop a couple of drops of food coloring in the middle, you can watch it and it'll be like, you can see that dark color in there in the middle at first, but after a while it will start to kind of dissipate and eventually it'll all be the same color. Cameron, do you have a question?
No, ma'am, I'm sorry. My cat walked across my computer.
That's funny how it, you know, my dogs usually come in here and bark, but I guess somebody's got food downstairs. So it goes from high concentration to low concentration, but it's kind of a cool thing you can try at home if you want to. Just put a couple of drops of food color in a clear glass of water, and you'll see it. And if you just leave it and don't disturb it, when you come back a few hours later, it'll all be smoothly the same color all throughout of whatever that color was. But in gases, we have another thing called effusion. Okay, and effusion is where molecules are going to escape through small holes into a vacuum. So if you've got a vacuum out, it will come out. Now, we also see effusion even if you don't have a vacuum. Okay, so like if you've ever bought one of those helium balloons, and you can, you know, like some of them are better than others, right? And like you'll get them, and you know they'll float. Because you've got helium inside, and helium is lighter than the air that's on the outside, and so it floats. And so after a while, though, if it was kind of a cheap one, like just a regular balloon, it'll start to kind of like sink where it's not floating as high, and eventually it just kind of lays there. That's because of effusion. Effusion is how the molecules are escaping through these little small holes, because even if you make something like a balloon or whatever, that material is going to have small little microscopic holes in it. And remember that the air molecules or the helium molecules are very small, and so they will find those holes and escape, because you know gases try to escape from wherever they are. And so the rate of diffusion and effusion of a gas are related to how fast those gas particles are going. Since they are, the velocity is determined by how big the molecule is, those smaller molecules like helium are going to be escaping a lot faster than if you had, you know, oxygen in the balloon, because oxygen would be 32 grams per mole, helium's only 4. So if you had a mixture of helium and oxygen, the helium would be the one that was finding those holes more often than the oxygen, because they would be moving faster due to their size. And that means that, so it's not a linear relationship, but the rate of that gas movement is inversely proportional to the square root of its mass. Okay, so the rate, the velocity, is proportional to 1 over the square root of the molar mass. And so it literally, it makes a huge difference, okay, this is having the square root. Mainly what you need to remember is what effusion is, okay? Effusion is where those molecules are escaping through those tiny holes that are in the material. All right, so diffusion versus effusion. Diffusion is where they're mixing together and getting as homogeneous as possible and as far apart from each other as possible. Whereas effusion is where they're escaping from that system through those tiny holes that are in the material. And it's proportional to the size of the molecule and how fast they're going. So if I heat it up, it's going to happen faster, because I'm making them collide with the walls faster and more often. All right, so we can't avoid stoichiometry, because that's what chemistry is all about. And so when we do stoichiometry in gas reactions, we're going to use the ideal gas law a lot of times to determine how many moles we have, because we're going to be given volumes. And if it's at STP, standard temperature and pressure, which is 0 degrees C and atmospheric pressure, don't forget that, then we can use the molar volume if we want to. Now, you don't have to, but you can. And so there are multiple ways to work these. So just because I work it one way, if you see it work another way, I don't care. If it works, that's fine, because like I said, there's multiple ways to do these, but I find that confuses people if I describe all the ways to work something. So I usually just give you what I have figured is the easiest one, okay, or the simplest one to understand. All right, so gases in a chemical reaction. So we've got methanol. We're making methanol. So we're synthesizing that from carbon monoxide and hydrogen gas and doing a bunch of other stuff to it, right? What volume in liters of hydrogen gas at a temperature of 355 Kelvin and a pressure of 738 millimeters of mercury do we need to synthesize 37.6 grams of methanol? When I see grams, I think moles, right? Grams, think moles. All right, so that's kind of my PV equals nRT, because whenever I have to find moles, that's the N in that formula. So I take inventory first, of course, and I have, I'm looking for liters. I have a temperature of 355 Kelvin. I have a pressure of 738 millimeters of mercury, so that's my pressure. And I have 35.7 grams of CH3OH. All right. So, and so I'm looking at grams, so I'm thinking moles. So I know I'm going to need N. So I need to know what the formula weight of methanol is, because I'm going to have to get that grams to moles. So it's actually 32. So 1 mole, because that's 12 plus 3 plus 16 plus 1. So that's 32 grams per mole of methanol. All right. Now, what I have to do, though, is I'm not really, okay, so if I was doing methanol, then that'd be fine. But what I'm doing is I'm doing liters of hydrogen gas. So I have to figure out how many moles of hydrogen gas that is. That's why this is a stoichiometric problem, okay? Because this is grams of CH3OH and moles of CH3OH, but I want hydrogen. So what do I have to do? I have to convert it to the hydrogen using the what? The molar ratio. Remember that? So I have 2 moles of hydrogen for every 1 mole of CH3OH. So that's going to give me 2.23 moles of H2. All right. I'm going to be using R, so I'm going to write that down. 0.821 liter atmosphere over mole K. All right, I've got K. I've got millimeters of mercury, so that's going to have to be in atmospheres. So 1 atmosphere is 760 millimeters of mercury. So 0.968 atmospheres. All right. So I've got pressure. I've got moles of H2. I've got temperature in Kelvin. So the only thing I have left is volume. All right. So PV equals nRT. So see how I found the number of moles stoichiometrically, okay, from this. So PV equals nRT. So V equals nRT over P. So V equals 2.23 moles times 0.0821 times 355 divided by the pressure in atmospheres, which is 0.968. And so the volume of hydrogen is going to be approximately, let's see, how many sig figs do I have? 3. Approximately 67.1 liters. Now, I've had some people get like 66.9 and things like that, but that's okay. As long as you have it set up correctly, it just depends on how many significant figures and how you round. So, but approximately 67 liters is the answer. So it's stoichiometric because I had to use the stoichiometric ratio of 2 to 1 because it wants hydrogen, but it gave me all the information for methanol. But if I know how it reacts from the balanced chemical equation, then I can go from methanol to hydrogen. So y'all would have just done a beautiful job of telling me how many liters of methanol you had, but that wasn't what the question was asking. So just always check, make sure that you're calculating what it wants. Practices for this one. Okay, so when you are okay, so this problem is at STP. Okay, when you see STP, go ahead and write temperature equals 273 Kelvin or 0 degrees C, right? And the pressure is going to be 1 atmosphere. And you have a volume of 1.24 liters, all right? And you're reacting with O2, and you're wanting to know grams of water as you are reacting with O2. You can use molar volume to do this. However, if you just use straight up stoichiometry, you can just work it the same way that you did the other problems. If you want to do it the other way, that's fine. But I mean, you can just kind of be consistent. I'm wanting to know grams of water, so when I see grams, I think moles. So I'm going to need to know grams of water. Okay, and so it's given me what I need to figure out how many moles of hydrogen I have, right? So if I put that in there, I can figure out how many moles of hydrogen I have, and then once I do that, then I can put it in the stoichiometry using the ratios, and then figure out how many grams of water I have. Okay, so I have everything here. It's in the right units right now. I'm going to be solving first for N because it's wanting grams. So N of H2, all right, because I don't know what it is this time, so I can't do the conversion between the two gases until the end. All right, so N equals PV over RT. All right, I've shown you over and over how to rearrange that, so I'm not going to waste my time. All right, and so N of H2 is going to be the pressure. It's STP, so it's 1 atmosphere. And the volume, it told me, is 0.24 liters. And then 0.0821 and 298, right? No, 270, wait. Oh, sorry, STP for gases is 25, isn't it? Sorry, my bad. 298 times 298. The STP for other things sometimes is 0, so, but it should be 298 this time. Okay, so N of H2 is equal to 0.055 moles. That's of H2. And so to figure out moles of water, it's going to be the same actually, because their molar ratio is 2 H2O moles for 2 of H2. So it's 2 to 2 or 1 to 1. And then there's 18 grams of H2O in 1 mole. So that gives me about 0.99 grams of water. About a gram of water, actually. So again, with the stoichiometry, there are ways that you can do, you can go straight from, since it's at STP, you'd know what the volume was at STP, so you can just kind of plug it in there. I typically just do them with the stoichiometric. It works out the same way, and you're just doing it consistently. But if you look at the book and stuff, you will see that they use the 22.4 because it's STP. But what I find is if I stress that too much, then people try to use that when it's not at STP. And so it's a little confusing. So, all right, and there's your practice for this type. All right, so just summarize one more time the gases, because you've got to be able to identify the characteristics of the gases and also the postulates of the kinetic molecular theory as it applies to gases. So they expand completely to fill with whatever container they're in. They're going to take the shape of the container. Very low dense because there's lots of space in between the molecules. They are compressible, so I can push and apply pressure and decrease the volume, or release the pressure and increase the volume. Mixtures of gases are always homogeneous. They mix through diffusion until they are completely homogeneous. Now, we've been talking about ideal gases. Okay, so ideal gases are those that are at STP basically and meet our criteria, and then they follow our rules. But real gases, actually, in the real world, are not going to behave like we want them to all the time, right? So if they don't do that, then we're going to have to correct for them somehow. And here's how they change. When we look at the the reason, well, I'd say the times that they don't act like ideal gases is it either at really high pressure or really low temperatures. Okay, so that's when they are not going to be ideal. Very high pressure or very low temperatures. When we do ideal gas, we assume there's no attraction between gas molecules, and they don't take up really much space compared to the space that they're around. But when you lower the temperature enough, you slow them down enough to where they could attract to each other. And if you heat them up, you are causing them to have higher pressure, right? So as you do that, then that volume is going to go down. Okay, so they do start to kind of take up space if you compress them enough, and it's not a big difference. Okay, so like if you look at the molar volume, you actually see in non-standard conditions, or in standard conditions, you see they're pretty close to the 22.4. They vary just a little bit, but when you change those things where you either ramp up the temperature quite a bit, you can then see how they're going to be closer together, okay, as opposed to farther apart. And so once you start doing this, they deviate molar volume wise from the ideal gas law. So the ideal gas law becomes not as perfect for doing that calculation. So we have to correct for things when that's the case. And so Johannes van der Waals, you've heard his name before, right? He was a reaction guy. He modified the equation to fit the behavior of real gases at high pressure. And so he did two things. And these little things right here, this A and this B factor, those are van der Waals constants. And so there's a B van der Waals constant and an A. We're not going to do calculations with this to correct for the temperatures, but you are going to you do need to be aware of what they're correcting for. Okay, B is van der Waals constant B, and it is based on the size of the molecule, And so it's correcting for the volume of the particle. So it's correcting the volume. So it's V minus N times B, okay? So all of these come from PV equals nRT, but we're correcting for pressure on one of them and volume on the other, okay? So the A constant is the intermolecular forces, okay? Because when you heat them way up or you cool them way down or whatever, you are changing the interactions between the molecules. So what you need to know, these are different for every gas, okay? And so the B factor corrects for the molecular volume, and the A corrects for. So those are things that you need to know about the van der Waals equation. But you will not have to do calculations. Not on the exam. Now you may see some where they want you to do it in your homework and you just plug into the formula. It has to give you the table. There's an A and a B table, but you won't have to do these on the exam. You may have to do them on homework, okay? And I know most people would rather do it on homework than they would on the exam. So I choose to assess you that way. Okay, so that's all we have. So that is the end of the course material. So I really appreciate you coming and hanging with me today. We are done, basically. We're going to have the review. So please go through that review. Try to work those problems. See what you know and what you don't know. What you have problems with or you want me to work, then I will work those during the review. And so I believe that happens on Wednesday, and then you'll have a week to take your test. So you'll, if you, as soon as we do the review and you feel like you're good, then you can go ahead and take your test. Remember, you have a quiz that's due, and then you'll have the exam, which is going to have the math problems. So anybody have any questions about anything? All right, I'm going to stop recording.